This video is going to be a content summary of COMP4920 based off publicly available readings and my personal research and notes. Alright. Ethics is the study of moral principles guiding human conduct. It can be framed as second-order reasoning about morality itself. Normative ethics focuses on what actions are right or wrong, whereas meta-ethics examines what morality itself is. For example, utilitarianism judges an action by its results, aiming to maximize overall happiness. Deontology, by contrast, judges actions by moral rules or duties, regardless of the outcome. Virtue ethics emphasizes the agent's character and virtues over specific acts. So each approach offers a lens for evaluating professional behavior in IT, from the consequences of technology to adherence of duties to fostering virtuous engineers. Let's look at three normative ethics that are central to this discussion. Utilitarianism is consequentialist ethics and says that an action is right if it produces the greatest good for the greatest number of people, usually measured by happiness and welfare generation. It is inherently teleological, focusing on outcomes, such as a recommendation system that maximizes user satisfaction. Deontology is duty-based ethics. Actions are either right or wrong according to moral rules or duties. For example, one must not lie or cheat ever, regardless of consequences. Kant's categorical imperative states, act only on maxims you could will to be universal law, and that's a classic example. Virtue ethics focuses on developing moral character and virtues. Rather than following rules, it asks, what would a virtuous engineer do in this scenario? Integrity and responsibility are two virtues that primarily guide professionals to do the right thing instinctively. Professional societies issue codes to guide conduct. For computing, the ACM Code of Ethics is central to this idea. It consists of general ethical principles that state, contribute to society and human well-being, avoid harm, be honest, respect privacy, respect intellectual property, and so on. And it also consists of professional leadership and compliance principles. For instance, ACM emphasizes that a computing professional must place public interest first, avoid harm, be fair, and take action on being wronged, respect privacy and confidentiality, and honor intellectual property. In practice, this means software engineers should prioritize user privacy by deleting data securely and always report unethical use of their products. Rather than treating technology as value neutral, modern ethics stresses value-sensitive design, aka VSD. VSD advocates that human values are built into technology from the ground up. As Batya Friedman notes, alongside traditional goals like reliability or efficiency, we need design criteria that embody or help foster core human values. In practice, this involves number one, identifying stakeholders who will use or be affected by a system, and number two, eliciting those stakeholders' values through interviews, surveys, participatory design, to name a few. And number three, iteratively designing systems that respect those values. For example, a social media platform might be designed with fairness by ensuring its algorithms do not systematically disadvantage certain groups. Similarly, human-centered AI emphasizes maintaining high levels of human control over AI systems so that they support and empower users. Schneiderman's HCAI framework argues for designs with both high automation and high human control, yielding systems that are reliable, safe, and trustworthy, and that amplify human creativity. Algorithms learn from data that often reflect societal biases, leading to algorithmic bias. Beza Yates warns that human tendency of favoring one opinion over another creates biases in all aspects of life, including web content and systems. Search engines, recommendation systems can thus perpetuate and amplify bias, unless they're thoroughly checked. And as researchers have found, online systems often mirror existing stereotypes or disproportionately target certain groups. Tackling these sorts of bias requires, first, awarenesses of the biases, then technical measures, and then the design choices. However, fairness itself is not a single concept, neither it is a simple concept, because different fairness definitions can conflict. Friedler, Scheidegger, and Venkata Subramanian highlight that various fairness criteria correspond to different underlying assumptions about the world, and often cannot all be satisfied simultaneously. In other words, making an AI fair to one demographic group can unintentionally harm fairness for another if the definitions clash. That's known as an impossibility theorem in algorithmic fairness. One cannot maximize accuracy and all these other criteria all at once without imminent trade-offs. Thus, professionals must carefully choose which fairness criteria best match the use case. So for example, prioritizing no false negatives in a medical diagnosis over demographic parity, and documenting those ethical decisions would be a good use case. Many systems operate as black boxes, making inscrutable decisions. Ethical practice calls for transparency and explainability such that stakeholders can understand and trust AI. However, explainable AI, called XAI, is still maturing. Malaysia and Paterno argue that current XAI tools do not meet expectations because explanations are not one size fits all. What I mean by that is, an explanation that's useful to a developer may not satisfy a layperson. Moreover, some believe there is a trade-off between accuracy and interpretability, though recent work shows certain interpretable models can match the performance of black box models on several tasks. In practice, achieving trustworthy AI involves a combination of techniques. Using inherently interpretable models where possible, providing user-tailored explanations, and most importantly, rigorous testing of AI systems in real scenarios. Ethically, designers should document AI decision processes and allow audits, because if a model affects someone's life, that person should be entitled to receive a clear, understandable reason for the outcome, or an appeal mechanism even. We often ask, who is accountable when automated systems cause harm? Research indicates a fundamental tension among fairness, accountability, and transparency in automated decision-making. And Sequoia Grayson argues that those three fundamental tensions can form a satisfiable triad in human-led decisions, but an unsatisfiable triad in fully automated systems. In other words, trying to optimize one often undermines another. For instance, highly complex deep learning models might achieve high accuracy, but they're going to be inherently opaque, making accountability hard. And this suggests a human-in-the-loop approach. For high-stakes decisions, humans should remain part of the process so that moral and legal responsibility has a clear place. System designers should build in checkpoints or override options and clearly assign responsibility among the team. And when no clear human agent can be pinned as responsible, a legal responsibility gap arises, and that must be addressed by policy, such as regulations requiring explainability or insurance for AI risk. Now, professionalism in IT isn't just about technical skills. It focuses on ethical character. Leaders especially should cultivate self-awareness and reflective learning. Ashford and DeRue describe mindful engagement as an active form of leadership development. Instead of passively reflecting, mindful engagements involve setting learning goals and experimenting with new behaviors in unfamiliar systems. In other words, engineers and managers should purposefully practice ethical skills, say by role-playing an ethics dilemma, and seek feedback, and use all that to iteratively improve. Crucially, leadership is seen not as a title, instead, a state of being shaped by one's mindset during experiences. Ethical professionals should therefore continuously cultivate virtues in themselves and their teams. Principlism is a core professional ethics framework that emphasizes core ethical principles that guide judgment. In fields like bioethics, Beauchamp and Childress identified four main principles. 1. Respect for the autonomy. 2. Beneficence. 3. Non-maleficence. And 4. Justice. Although these arose in medicine, they do apply broadly. For a software engineer, this means respecting user autonomy, maximizing benefits, minimizing harm, and distributing burdens and benefits equitably. Principlism does not solve every dilemma by itself, but it does provide a toolkit. Because when principles conflict, one must weigh them contextually. Professionals may face situations where unethical practices occur. Let's say that someone discovered a colleague secretly collecting user data. Ethical codes like the ACM mentioned before encourage reporting violations of the code to appropriate authorities. Whistleblowing is a serious step that should follow internal channels where possible, but ultimately aims to protect the public interest over company loyalty. It embodies the ethical virtue of courage and the duty to avoid harm. A responsible professional will document concerns and seek guidance and, if needed, escalate issues to a higher management or ethics committee, always acting in good faith to correct problems. We all know that AI is growing more powerful and imminent, and AI safety and value alignment thus become urgent. Superintelligence, which is AI vastly smarter than humans, is a concern highlighted by Nick Bostrom's Superintelligence article. Fears that it might one day take over the world and destroy humanity have entered mainstream discussion. However, current state-of-the-art AI like newer GPT models or image models are still far from true general intelligence. Empirical studies show that modern language models often fail basic reasoning tasks, so they act more like a complex pattern matcher than self-aware reasoner. Many experts therefore judge that superintelligence is not imminent, although controversial. Even so, value alignment remains critical because ensuring AI systems pursue human-aligned goals should be in humanity's best interest. Gabriel and Ghazavi stress that alignment must account for the plurality of human values worldwide. They link the AI alignment problem to long-standing issues in fairness and participatory design. In practice, that means involving diverse stakeholders in AI design, echoing VSD, and designing mechanisms that allow broad value input into AI objectives. For example, setting up governance bodies with public representation to oversee AI policies, or using multicultural ethical datasets in AI training. Munn offers a sobering critique of the AI ethics movement. He argues that most corporate and academic AI ethics initiatives are toothless principles that do not constrain the tech industry. In other words, mere codes and statements often lack enforcement or serious reform, and that allows companies to claim ethical concern without changing their behavior. Munn says this focus on high-level principles can distract from real solutions, and this urges systematically thinking about power and oppression instead of tick-box ethics. The takeaway for students is to be critical. Know that ethics must translate into hard commitments, regulations, oversight to have some effect, instead of just being a slogan. Let's get to meta-ethics, arguably the most difficult conceptual branch of ethics. Meta-ethics examines the nature of moral claims themselves. It asks, are moral truth objective or relative? How do words like good get their meaning? While not applied ethics per se, meta-ethical awareness helps IT professionals appreciate debates about whether moral norms are universal. For example, one might debate if data privacy is a universal good, or if it depends on cultural context, relativism versus realism. Understanding meta-ethics sharpens awareness of deep disagreements about right and wrong in technology use. a cutting-edge topic is moral responsibility for autonomous systems. Taddeo and Blanchard address the responsibility gap for autonomous weapons. They suggest that developers can take a moral gambit where they knowingly deploy an autonomous weapon system, AWS, with uncertainties about its behavior, but they accept full moral responsibility for whatever happens. In other words, that would be betting that the AWS will behave correctly, yet vow to be answerable if it does harm. Importantly, Taddeo and Blanchard argue this gambit can be acceptable for non-lethal AWS, such as surveillance drones, but not for fully lethal weapons. Practically, this implies that for life-critical autonomous technologies, human responsibilities can't be offloaded entirely because strict human oversight or banning of fully autonomous lethal systems are required. Cybersecurity professionals face unique ethical issues, naming a few being privacy, hacking techniques. McNeish and Vanderham highlight that current ethics governance in cybersecurity is insufficient. They note two communities, one being academics or researchers, and two being practitioners, aka industry professionals. Academics often have research ethics boards for oversight, but that may not understand security research's special challenges, and practitioners usually have no formal oversight at all. This gap is highly alarming given the stakes. Cybersecurity failures can endanger infrastructure and privacy. So the authors recommend the following. Enhance ethics education in computer science curricula so developers recognize security ethics issues. Effective codes of conduct for cybersecurity professionals with clear guidelines on responsible practices. An active dialogue and communication in the community about ethical challenges, treating ethics as an ongoing conversation, something that can be applied to all branches in life. And overall, the field needs to treat cybersecurity as an ethical practice area instead of a mere technical problem that many have been viewing it as. Well, that's it for my summary. I do hope that this does help in any shape or regard, and I'm hoping that in the final exam next week, I'm able to achieve a full mark to get 100 RAM for this course. That's all.